In this video, we will see memory management unit, physical and logical address space, and paging in memory management and page table property. Here, the purpose of memory management unit is to convert the logical address into the physical address. The logical address is the address generated by the CPU for every page, while the physical address is the actual address of the frame where each page will be stored. When a page is to be accessed by the CPU by using the logical address, the operating system needs to obtain the physical address to access that page physically. The logical address has two parts: page number and page offset. Memory management unit of operating system needs to convert the page number to the frame number. The mapping from virtual to physical address, here virtual means logical, virtual to physical address is done by the memory management unit, which is a hardware device, and this mapping known as paging technique. The physical address space is conceptually divided into a number of fixed size blocks called frames. The logical address space is also splitted into fixed size blocks called pages. So page size is equal to the frame size. And physical address and logical address spaces. So as we know, we will earlier seen pages is logical addresses. Logical address space is divided into pages and physical address space is divided into frames. Physical address space in a system can be defined as the size of the main memory. It is really important to compare the process size with the physical address space. The process size must be less than the physical address space. So physical address space is equal to the size of the main memory. If the physical address space is 24 kilobytes, now this 64 kilobytes, this 64 kilobytes is going to be represented as bytes, 2 power 16 bytes. And the word size is 8 bytes, and this 8 bytes will be represented as 2 power 3 bytes. Now we are going to see the number of bits required to represent physical idea. Hence, the physical address space in words is equal to divided by address space, logical address space in bytes. 64 kilobyte is represented 2 power 16 byte. This physical address space divided by word size 2 power 3. 2 power 3 will give you 2 power 13 words. So this 13 is the bits, number of bits required to represent physical address. In general, if physical address space is equal to n words, then physical address is log to n. And the logical address space can be defined as the size of the process. The size of the process should be less than, so that it can reside in the main memory. So consider this logical address space is equal to 128 MB, and this will be represented as 2 power 27 bytes. And the word size is equal to 4 bytes. This will be represented as 2 power 2 bytes. Now we have to calculate the number of bits required to represent logical address. So 2 power 27, which is the logical address space in bytes, divided by 2 power 2, which is the word size represented in bytes, will give you 2 power 25 words. So logical address needs 25 bits to represent logical addresses. In general, if logical address space is equal to L words, then logical address is equal to log to L. And then paging. Now we have seen logical address, physical addressing. Paging is a memory management scheme that eliminates the need for contiguous allocation of physical memory. This scheme permits the physical address space of a process to be non-contiguous. Logical address or virtual addresses, which is represented in bits, is an address generated by the CPU. And logical address space or virtual address space represented in words or bytes is the set of all logical addresses generated by a program. Physical address, which is represented in bits, is an address actually available on memory unit, which is a actual memory. Physical address space, which is represented in words or bytes, is the set of all physical addresses corresponding to the logical address. The main idea behind the paging is to divide each process in the form of pages. The main memory will also be divided in the form of frames. One page of the process is to be stored in one of the frames of the memory. The pages can be stored at the different locations of the memory, but the priority is always to find the contiguous frames or holes. Pages of the process can are brought into the main memory only when they are required, otherwise they reside in the secondary storage. Address generated by the CPU is divided into page number. This logical address. Logical address is generated by the CPU is divided into page number and page offset. Page number is the number of bits required to represent the pages in logical address space or page number. Page offset is the number of bits required to represent particular word in a page or page size of logical address space or word number of a page or page offset. Physical address is divided, actual address is divided into frame number and frame offset. Frame number is the number of bits required to represent the frame of physical address space or frame number. Frame offset is the number of bits required to represent particular word in a frame or frame size of physical address space or word number of a frame or frame offset. Here, the hardware implementation of page table can be done by using dedicated registers. But the usage of registers for the page table is satisfactory only if page table is small. If page table contains large number of entries, then we can use TLB, transaction look aside buffer, which is a register, a special small fast lookup hardware cache. The TLB is associative high speed memory. Each entry in translation look aside buffer consists of two parts, a tag and a value. When this memory is used, then an item is compared with all tags simultaneously. If the item is found, then corresponding value is returned. Here you can see the logical addresses is generated by the CPU, and this is the page number. If the page is found in translation look aside buffer, then it is a hit. Hit means the page is found in the cache, so we don't have to go for the page table or main memory. Page table is loaded in main memory, so we don't have to access the main memory. So if the page is available in translation look aside buffer, then it's a TLB hit. If not found, then we have to go for page table loaded into the main memory, which means that TLB miss. The page is not found in the cache, which means it's loaded into the page table, so it is TLB miss. And then it's loaded appropriate with the frame number and the frame offset, and it can go for physical addresses. This is how the logical addresses is converted into the physical addresses. What we have to remember, the logical addresses is generated by the page. If the page is found in cache, translation look aside buffer, then it is a TLB hit. We don't have to go for page table loaded into the main memory. If not found in the translation look aside buffer, then we have to go look for translation look aside buffer first. If not found, again we have to go for page table or page map. This is how we are going to found the logical addresses and physical addresses. Here, if here the first rule here, which represents the rule to be if the page is found on TLB. The page is found on TLB, we have to use this effective access time rule here. Main memory access time is equal to M. If page table are kept in main memory, effective memory access time is equal to M for page table plus M for particular page in a page table. Here this rule is applicable if the page is found in translation look aside buffer. If not, then we have to use this second formula. Transaction look aside buffer access time is equal to the transaction look aside buffer hit ratio. It means the the page is found on the TLB X, then the miss ratio is equal to 1 minus X. Effective access time is equal to hit ratio multiplied by C, which is the TLB access time plus memory access time plus miss ratio, the number of ratio the file, the page is not available in the TLB, multiplied by C, which is a TLB access time plus memory access time plus for table access, for main memory access and for page table access. So we have to remember this formula to calculate the effective access time. And the page table entries in page table, or page table has page table entries where each page table entry stores a frame number and optional status bits. Many of status bits used in virtual memory system. The most important thing in page table entry is frame number. So other than the frame number, all these entries are optional. The page table entry has frame number, which is required number, and then present or absent bit, a protection bit, reference bit, caching bit, and then dirty frame number. The important part of the frame, it gives the frame number in which the current page you are looking for is present. The number of bits required depends on the number of frames. Frame bit is also known as address translation bit. So the number of bits for a frame is equal to size of the physical memory divided by the frame size. And then present or absent bit, which the present or absent bit says whether a particular page you are looking for is present or absent. In case if it is not present, that is called page fault. It is set to 0 if the corresponding page is not in memory, used to control page fault by the operating system to support virtual memory. Sometimes this bit is also known as valid or invalid bits. And then protection bit says that what kind of protection you want on that page. So these bit for the protection of the page frame, read or write access. Referenced bit will say whether this page has been referred in the last clock cycle or not. It is set to 1 by hardware when the page is accessed in the last clock cycle. And then caching enabled or disabled bit. Sometimes we need the fresh data. Let us say the user is typing some information from the keyboard and your program should run according to the input given by the user. In that case, the information will come into the main memory. Therefore, main memory contains the latest information which is typed by the user. Now, if you try to put that page in the cache, that cache will show the older information. So whenever freshness is required, we don't want to go for caching or many levels of the memory. The information present in the closest level to the CPU and the information present in the closest level to the user might be different. So we want the information has to be consistency, which means whatever information user has given, CPU should be able to see it as fast as possible. That is the reason we want to disable caching. So this bit enables or disables caching of the page. And then modified bit, also called as dirty bit. Modified bit says whether the page has been modified or not. Modified means sometimes you might try to write something on the page. If a page is modified, then whenever you should replace that page with some other page, then the modified information should be kept on the hard disk, or it has to be written back, or it has to be saved back. It is set to 1 by hardware on write access to page, which is used to avoid writing when swapped out. Sometimes this modified bit is also called as dirty bit. So that's it for paging in memory management. In next video, we will see segmentation in memory management.